So I want to give an example of this structural induction that I was talking about. But before we do that, let's introduce some terminology that we will need. So if we have a binary tree, and inside that tree we have some piece of it that looks like this, you can see that these are sort of the basic units of our binary trees. Then when we're looking at this kind of relation, we call this guy the parent, and we call these two the children. So saying that it's child just means that it's below that node in the tree. So a node with no children is called a leaf, which of course you can understand in the tree metaphor that you may have branches and branches and branches, but when you reach a leaf, that is the end. There's nothing after that. That is the end of the tree. So that is why it's called a leaf if it has no children. And a node with children is called an internal node. For, mostly obvious reasons that it is not at the end. It is on the inside in some sense. So let's do a quick example. If we have a binary tree that looks like this, I guess I don't need to copy this from my notes. I could just draw whatever, but may as well copy it from my notes so that I feel good about myself. Then let's say the leaves, what's the best way to draw it? So the leaves are the guys at the bottom that have no children. So these are the leaves. And we'll say these are the internal nodes. And that is everything else. So this, and this. So in this case, this tree has, let's see, 5 internal nodes and 6 leaves. So the number of leaves is 1 more than the number of internal nodes. And that actually is a fact about all binary trees. So let's prove it. So claim, and let me emphasize that a binary tree, I'm gonna say that because I'm gonna get tired of saying full binary tree every time, but a binary tree in general is slightly different from this. We're talking about full binary trees. So the claim is, if a full binary tree has L leaves and I internal nodes, then L is equal to I plus 1. So our proof will be by structural induction. Which is to say, using recursive definition of binary trees. So the base case, we have a tree with a single node In this case, it is a leaf node because it has no children. So L equals 1 and I equals 0. So L equals I plus 1. Checks out. So induction step. Now again, it's going to have slightly a different texture than regular induction. So we're not going to say suppose it's true for, 0 less than or equal to k less than n, or anything like this. But we're going to use the recursive definition of binary trees. So we're going to consider this tree, which is how we make new binary trees for old ones. And we're going to assume that the thing we're trying to prove is true for these component parts that we're using to build the tree. So assume true for T1 and T2, i.e. L1 equals I1 plus 1, and L2 equals I2 plus 2, plus 1, where these are the number of leaves and internal nodes of each tree. So T1 has L1 leaves and I1 internal nodes. And similarly, T2, L2, I2. So sort of similar to how we were thinking about height, let's consider if we have this tree, how many leaves and internal nodes does it have compared to these trees that we made it out of? So let me give this thing a name. So I'll call it T. Then, so let's say T has L leaves and I internal nodes. Then how can we write L in terms of L1 and L2, the number of leaves of T1 and T2? Well, we have, no new leaves because this one node that we're adding is not a leaf. And if we have any leaves in T1 and T2, they will stay leaves in these trees because we are not adding any children. So the whole number of leaves is just the sum of the leaves in the two parts. And what about the internal nodes? It's basically the same. Internal nodes here will remain internal nodes, and the same here. The difference is that this thing is a new internal node. So I is equal to the sum of the smaller trees plus 1. Plus 1 for this new guy. So now we can combine these formulas with our inductive hypothesis and say L, which is equal to L1 plus L2. Well, by the inductive hypothesis happening here, we know that this is I1 plus 1 from this guy, and I2 plus 1 from this guy. But now, I is equal to I1 plus I2 plus 1, So this whole thing is equal to I plus 1, which is to say L is equal to I plus 1 as desired. And that completes the structural induction, because this is our sort of recursive step for making new binary trees out of old ones. So having proved it for the base case of a single node, and having proved it for this sort of recursive step of defining a new binary tree, since every binary tree is built in this way, we conclude that the result is true for all binary trees.